Welcome to the HVAC Engineering-Techie channel. This is the channel where we talk all things HVAC. We talk engineering design, we talk construction, we talk equipment, we talk systems, we talk test and balance extensively, we talk about controls, and we talk about efficiency and performance of systems. These videos are intended to be educational devices for you to be able to advance your career. So today we're going to talk about HVAC electrical calculations, and this is how you calculate how much energy your system's using, different aspects of maybe design for electrical of HVAC systems. So before we do that, I'd like to ask you a big favor, and I'd really appreciate it if you would subscribe to the channel by just hitting the subscribe button down below and the like button, the thumbs up. They're perfectly free. They cost absolutely nothing. It doesn't, when you like the button, you subscribe, I'll never bug you. I don't have any way of doing that anyway, but I wouldn't do that. And the reason it's so important to me is that Google, that's how they evaluate this video on how it's doing on their platform. So that can really help me, and I appreciate it if you do that. So let's get started talking about electrical calculations. All right, let's talk about electrical calculations. Okay, amps. The formula for amps single phase is horsepower, what horsepower is known, is horsepower times 746 divided by E, which is in electrical is voltage, times percent efficiency of the motor times power factor. For three phase, it's the horsepower times 746 divided by the voltage times efficiency times the power factor times 1.73, and that's the three phase. Now, phases matter because it uses different current amounts depending on, for the same amount of work, it takes more to do a single phase than it does three phase. So where kW is known, it's amps equals kW times 1,000 over E times PF, the power factor again. And in three phase, it's kW times 1,000 divided by E, power factor times 1.73 again. And then where KVA is known, now KVA is the apparent power. It's volts times amps. It's the actual power that the power factor skews. So it's that angle of the power factor. It's that apparent power. You don't use it much. You probably won't ever calculate it unless you're trying to design something. If you're designing wire and everything, you need KVA, but otherwise, for us in the field doing mechanical systems, KVA doesn't matter much to us. But anyway, the formula is KVA times 1,000 over voltage, or three phase is KVA times 1,000 over voltage times 1.73. So let's do some calculation, some examples. An 89% efficient 120 volt single phase motor with 2.5 kW and a power factor of 0.87, what will be the amps of the motor? Okay, now if you're doing a calculation from a drawing, or you're doing a calculation from measurement of the field, power factor may be difficult for you to figure out what that is. You can measure power factor, but you have to have a power quality meter to do that. You can't get power factor from a regular handheld voltmeter. So power factor can be somewhat difficult. Now some machines will list the power factor on it, but that's the design power factor of the product, like a UPS or something. So what you need to do is try to guess what it is. Now, if it's 0.89, that's a really good power factor. Power factor 1 would be perfect, right? But you're never going to get, as long as you got a motor in the circuit, you'll never get 1. Because the motors, actually induction motors, kind of screw up power factor a little bit. And so do other devices, but mainly motors. So basically, if you're guessing power factor, guess somewhere between 8.86 and 0.89. You'll be safe. 0.89 is a nice safe number. That's a good power factor, right? If you get down to by 0.81 or so, they really need to pay attention to that because they need to correct it. The reason is the lower the power factor, the less work the power does. So that now people are paying for power, not getting the benefit of it. So it's really important. And they use capacitors to bring the power factor back into line. Electronics actually also does it. So a VFD can actually be used to increase the power factor because it's adjustable. So anyway, you can do this. So let's do this formula. So we're using kW times 1,000 over E times power factor. You get 0.25, which is a kW times 1,000 over 120 volts. Now also, when you're doing this in the field and you're doing a field measurement, you need to use the actual measured voltage. Maybe 119.8 or something. It almost never be 120. You're using 120 when you're in the office doing a calculation and you don't know. But especially if you're trying to do energy calculations, you need to use the actual voltage in amps that you actually measure. That's very important. So this equals 23.95 amps. So that's what that circuit will do at that power factor. Example 2, a 96% efficient 480 volt three-phase motor with 34.5 brake horsepower and a power factor of 0.89. What will the amps be of the motor? Okay, here again, same thing, but the three-phase equation. So that's going to equal 34.5, which is the brake horsepower, times 746 over 460. Again, you need to measure the exact voltage. And on a three-phase system, what you do is you measure the voltage of all three legs and you average them to get this number. But always measure all three legs so you know exactly what it is. If you just measure one leg and say that's the amps, you'll be wrong. So you need to use the average of all three, times 0.96, which is the efficiency, times 0.89, which is the power factor again, times 1.73, and that equals 37.85 amps. Now, if you'll notice that this is a bigger motor. Now, one thing about motor efficiencies, the bigger the motor, the higher the efficiency normally. So you can be up to these 97% efficiencies on bigger motors, 98% on a big motor, but never on a little motor. Little motor efficiencies get terrible. I mean, down fractional motors can be 0.65, 0.66. The 60% efficiency, much less, because they're just not capable of getting high efficiencies in the motors we buy anyway. There might be really efficient motors out there that I don't know about, but the standard motor we buy is not that efficient on even a premium efficient small horsepower motor is not very efficient. So kW, where amps is known, so the single phase is kW is voltage times amps times power factor over 746. Two phase is kW is E over A times power factor times 2 divided by 1,000. And three phase is E times A times power factor times 1.73 over 1,000. Okay, what's two phase? Well, two phase is when you have two hot wires coming into a device like 240 volt. 240 volt is actually a two-phase system. So, and three phase, of course, the three wire, this is a two wire, and this is a single wire and a neutral, which is, it's not two wire. This is a single phase. It's got one wire and a neutral. This has two phases, an A and B. Well, this is an A or a B or a C and a neutral. This one's A, B, A, C, C, B. Who knows? And three phases, all three of them, of course. Let's do an example. Find the kW of a 460 volt three-phase motor drawing 9.25 amps with a power factor of 0.84. So kW is E times A times power factor times 1.73 over 1,000. So it's 460 times 9.25 times 0.84 times 1.73 over 1,000. 6.18. A 120 volt single phase motor draws 10.4 amps with a power factor of 0.89. What will be the kW of the motor? So the kW is E times A times power factor divided by 146. So it's 120 times 10.4, which is the amps, times 0.89, which is power factor, 746, 1.49 kW. So when you're in the office and you're trying to figure out a calculation and you don't have actual data, I always just take a motor catalog and look up a motor that is the motor we're going to be using, and it'll show the efficiency for that motor. Rather than guess, it's easier just to look up a catalog. I always used it. That's what I use my Granger catalog for. 3 inches thick, but still that's what I use it for. Okay, KVA. This one you won't use very often, but single phase KVA is E times A over 1,000. Two phase is E times A times 2 over 1,000, and three phase is times a 1.3 divided by 1,000. Find the KVA of a 120 volt single phase circuit drawing 9.25 amps. So it's pretty simple. It's KVA is 120 times 9.25 amps with 1,000 is 1.11 KVA. All right, brake horsepower. This is one you'll use a lot. So single phase brake horsepower is voltage times amps times percent efficiency times power factor divided by 746. Brake horsepower is voltage times amps times percent efficiency times power factor times 2 divided by 746. And three phase is the same, times 1.73 divided by 746. All right, let's do a calculation here. An example. Find the brake horsepower of a 68% efficient 120 volt single phase motor drawing 9.25 amps with a 0.89 power factor. So voltage times amps times percentage efficiency times power factor. So that would be 120 volts times 9.25 amps times 0.68 efficiency, which is reasonable for a small motor, times 0.89 divided by 746 is 0.9 brake horsepower. So it's fractional horsepower motor. You will find the brake horsepower of a 95% efficient 460 volt three-phase motor drawing 24.6 amps and a 0.89 power factor. Again, a bigger motor, much higher efficiency. So it's voltage times amps times percent efficiency times power factor times 1.73 divided by 746. And all of that equals 22.19 brake horsepower. So these formulas are really easy to do. Just have to remember the formula. Now, I normally keep an Uglies book with me, and Uglies is a little yellow, probably 3 by 2.5 inches little book, and it has all the electrical calculations in it. And so that's handy to keep with me, and because I don't keep these in my memory banks, so it's easier to look these up. Okay, voltage drop. So voltage drop is important if you're in construction. And the engineer is supposed to lay all this out, but a lot of times there's a lot of things engineers don't lay out, like control voltages. So if you have a transformer for a controller and you're going to run a wire out to it, and you run it for very long, or vice versa, you have an electrical circuit designed for a transformer for a controller, and it goes right there, but the controller is 100 feet away. The wire, that 24 volt wire from that transformer to that controller, it's very important that it be sized correctly. And engineers don't, the design engineer of the project doesn't do that. That's designed by the control contractor. So we need to figure that out. So voltage drop is, the voltage drop equals 2 times K times L times A over circular mils. So K, there it is. Okay, K is the resistance in ohms, and it's 12.9 for copper and 21.2 for aluminum wire. So these are standard factors, K factors, and so you'll use 12.9 for copper. Hopefully you're not using any aluminum wire anymore. The reason we don't use aluminum is because it expands and contracts so much that the bolted connections become loose. Copper can do the same thing, but not like aluminum. So anyway, that's a K factor. L is the one-way length of wire. So in other words, if you're 100 feet away, you're going to run 100 foot of wire out to a device. Remember that it actually has another wire coming back, but you can ignore the wire coming back. It's the one-way length of wire. And CM is a circular mils. So it's kind of a strange notation, but it's the area of the copper wire. So if you have an aught wire, it's much bigger than a number 14 wire. And this is a table up here of circular mils. You can see a number 1 wire is like 60,000 or so, 61, I think that's 81,000. So that's a lot of circular mils. I don't know exactly the definition of circular mil, but this is the table for circular mils, and it's an area. So this is the voltage drops, and this is how to calculate CM, circular mil. So it's 2 times K times L times amps over voltage drop equals a circular mil. So basically I use this one most of all the time. Anyway, so let's go do an example. So find the voltage drop for number 8 copper wire, 460 volt 3-phase circuit carrying 35 amps for a motor that is 150 feet from the starter. By the way, that's a long ways from the starter. Possible, but not very likely. Normally the starter needs to be a lot closer, but this is just an example, so we'll look at that. So we got voltage drop equals 1.73 times K times L times A. So it's 1.73 times 12.9 for copper wire times 150 foot length times 35 amps. So that's the amps over 16,500. So it's number 8 wire, and if you look it up on that table in the last sheet, 16,500 is the circular mils for number 8 wire, and it comes up to 7.1 volts. Okay, what does that tell you? Well, here's what it tells you. 7.1 divided by 460 equals 1.54%. And the codes say that the voltage drop should be under 2% for branch wiring. Main wiring can get by with 3%, but 2%, and it's all about droop. They don't want the voltage dropping below the minimum accepted voltage. And so this 7.1, if you have 460 volts, that's going to be 453 or so. So if you have 480 volts, it's going to be 473. So it's plenty. The minimum voltage would be 440, of course. So it could be no problem. Okay, let's do another example. Find the voltage drop for a number 14 copper wire, 120 volt single phase control transformer circuit drawing 7.4 amps. That is 240 feet from the breaker. Okay, now that's way too far, but we're trying to make a point here on this example. So the voltage drops 2 times K times L times A over Cm, so it's 2. 2 times 12.9, which is copper wire again, times 240 feet, times 7.4 amps divided by 4,110, which is a circular mils for number 14 wire. And you get 11.5 volts. Well, 11.5 on 120 is 9.29. That's not going to be acceptable at all. That's way too high. So now we have to pick another wire. That wire is way too small. Now, what you could do is you could work your way out from 12 to 10 to 8, but I kind of jumped the gun on it and went right to 8. So basically you have a 2 times 12.9 over the 240 times 7.4 with the circular mils for number 8 wire, which is 16,500, which equals 2.78 volts. Well, what does that look like? Well, it's 2.32%. Now that doesn't actually meet the 2%, but it's going to be okay because it's under 3%, and it would mean at 120 volts, we're going to get 117 volts, which is above the minimum voltage of 110. So this is how you do voltage drop. Voltage drop, normally you won't be worrying about it unless you got something weird happening and you got low voltage. Now, what happens when you have a low voltage to a motor? It basically makes the amps go high, and you can burn a motor with low voltage. So voltage is important in a higher voltage, but even these driving an actuator is a motor, and low voltage is kind of a problem. All right, that's it for electrical. That was pretty painless, pretty easy. So just make sure you have all the formulas handy. They're easy to work, and you'll have no problem with that. So again, please subscribe and like. I really appreciate it. And I hope you guys have a great day, and catch you on the next one.